So good afternoon. Thank you for joining us. Today, our speaker is Dr. Richard Signell. He's a research oceanographer from the USGS, and he has an abundant experience in physical oceanography and modeling. And today he's going to share some of his work on the Pangeo project with us. And at this point, I'll turn it over to Rich, and thank you for being here.
All right. Thanks, Anne. All right, I'm going to share my entire desktop. All right, so yeah, I'm kind of excited to talk to you about Pangeo. I think it's a movement, it's a community, it's a framework. I hope you find something in this talk that you think is interesting that would help your own scientific work. So it's got a kind of a long title. As I said, it's a community and a framework for flexible, scalable, open source geoprocessing. So the scalable part means you can run on as many CPUs as you have around. And as you'll see, it's hopefully something that doesn't look too different than the kind of thing you might be doing now. So I'm giving this talk. I'm Rich Signell, oceanographer at USGS, like Ann said, but really this is a much bigger project, and it was actually started by Ryan Abernathy, Joe Hammond, Matt Rocklin, a bunch of other folks, and a lot of the contributions to this project have been by folks other than me. In fact, I'm mostly a user, a scientific user of this project, although I am a member of the Pangeo steering committee. Everything sound okay so far?
Yeah.
Yeah. So I wanted to start off with the motivation for this project. So Ryan Abernathy is a climate oceanographer. So he's looking at large-scale ocean simulations. And this is a simulation that was done at NASA showing currents around the globe. And this simulation, or actually the most recent version of this simulation, of course, it's a numerical model, stored on hourly time steps for 1 year was 2 petabytes. So when you're thinking about how would you assess how well this model is doing, or how would you even start to explore this model, you're not going to be downloading 2 petabytes of data. Or if you are, it's going to take a long time. And so, you know, really what motivated this project was how can we as climate scientists come up with a system that would allow us to do collaborative, interactive exploration of data sets that are of this size. So, you know, I'm at the USGS. I don't do climate work, but I do supervise a group, which is a sediment transport modeling group. We do a lot of sediment transport simulations that involve a coupled modeling system called COAST, Coupled Ocean Atmosphere Wave and Sediment Transport Modeling System. The lead developer is John Warner. And so we have a lot of coupled models. We can do things like, this is Hurricane Sandy. You know, we're simulating wind and waves, water levels, seabed stress, seabed erosion. And typically, through all the simulations we do in our group, we have maybe a couple hundred terabytes of coastal model output. And it's all in these 4-dimensional netcdf files, similar to the data that came out of that global model. And how can we better work with this amount of data? We can store it locally, but what if our collaborators want to access this data? How could we share it with a wider community? So, you know, the traditional way we do data analysis, right, is we run a simulation somewhere, maybe at an HPC center, maybe at a local cluster our university or our institution has. And then we move the data through a big fat internet pipe, hopefully fast internet, right down to our desktop somewhere where we store them on hard drives. And we look at them with things like MATLAB or maybe Python or R. And we still do things pretty much this way. Thanks, Sebastian. Can you see that pop up? Okay. Anyway, hopefully I don't get too many of those. So, but what we'd like to do, you know, instead of downloading that data, as we just said, we're not going to download 2 petabytes of data, right? So what we want to do instead is we want to do our simulations in the cloud, leave our data in the cloud, and access and do our analysis and visualization in the cloud, and just use like our browser, or, you know, in this case, maybe we have a happy user sitting in the park with her hotspot and her Chromebook, and she's got a lightweight internet connection to the cloud, but she can do anything she needs to do, including analyze, terabytes of information. This is what we want to do. And, just one slide on, wait a minute, did you say like do simulations on the cloud? If you're a modeler, you might have heard people say in years past that we still need HPC centers because only HPC centers have fast enough network speeds to be able to do the communication between little chunks of model domain that need to communicate when you're running an ocean model in parallel. But this all changed in a year or so ago. Amazon and other cloud providers have been increasing their network speeds. And now this is from a slide from a talk by Daniel Arevalo, where he was running a Navy global model. And he was comparing these different lines or different machines that he was running on. So this was the Navy supercomputer, this green line here. And being lower on this means less wall clock, so faster times to actually get the simulation done. In this case, it was a 5-day long, 19-kilometer forecast for the globe. And he found that with the older sort of Amazon technology, the Navy is green here. And as you get to more and more processors, the green line here stays nice and along these ideal sort of scaling lines. So faster, more processors gives you, twice as many processors gives you twice as fast a model. The old Amazon sort of solutions and the things that you probably hear people still talk about started to tail off and basically stop scaling. But with this these new instance types and this new networking, you can actually get speeds on the cloud doing HPC, high performance computing, that are faster than on your supercomputer. And over here, he had a cost of doing this, this 5-day long global run. It was $44. So that's kind of a game changer. So we really can do end-to-end simulation, storage, model analysis, and visualization on the cloud. But I'm going to talk mostly now about the analysis and visualization part and show you that it's not just cloud. So if you're not ready for cloud, you can still use these tools. So Pangeo is a community. Actually, it's not really a product, it's actually a community that has a similar view of how software should be developed to enable science to go to the next level. And it's about open source. It's about using packages that have already been proven in the community. And so Ryan Abernathy, as I said, with those others, wrote a proposal to NSF, to the EarthCube program. They got some initial funding. They got a bunch of cloud credits from Google. So Lamont, UCAR, the British Met Office, and commercial software developers were all involved with this first proposal. So it's a really pretty powerful combination of people, scientists, technologists, and cloud providers. Since then, Amazon, NASA, a bunch of other groups, Microsoft, everybody's piled onto this project because they think it's the future. And it's really just snowballed since it started 3 years ago. One of the best things about this group is that it's really open. Everything is discussed out in the open in GitHub issues and now in discourse. And nothing, email transmissions between people about technological stuff happen all the time, but they're very much frowned on in Pangeo. So all the discussion is out in the open, and this makes things, of course, much more transparent and inclusive. So, as I said, it's not just something you install necessarily. It's flexible because really all it is a bunch of Python packages that were already working well in the community, and the Pangeo group is just making sure that they play nicely together and play nicely in these different situations, like on your local computer, at your HPC center, or on the cloud. And it's also exploring what it means to be performant in those different situations. So the key packages that I'm going to talk about today are are these ones in the circles: Jupyter, Xarray, Dask, and Holoviz. But there are these other packages like TensorFlow for machine learning, or PyTorch for machine learning, Pandas for tabular data, a bunch of other, anything in the Python ecosystem is really part of, quote, Pangeo. But this is sort of what a typical, deployment, I guess, the key elements here. So you have this Python environment in which you have Xarray. Xarray is a package that understands the netcdf data model. So, you can have variables with certain dimensions, and you can have a bunch of metadata so that you know that some variable called T is actually standard seawater temperature and things like that. And it also, beneath the hood, relies on this thing called Dask. And so it means that you can work with data in this environment just like it was netcdf files, but you can parallelize that automatically through this package called Dask. And if you store your data in chunks, so if you chunk your netcdf files or you chunk your other types of data files, then these different workers can read different chunks of data to do computations in parallel on your data. And so you can make things much faster, and you can read much more data so that you can start to do things with like terabytes of data. And I'll show you a demo in just a bit. So this other piece is Holoviz. This is a visualization package that allows you to write Python code, but it actually generates interactive JavaScript in your browser. And Jupyter is the part that allows you to actually just sit there and access this whole thing with your browser. So you type instructions in your machine here. Those just those instructions are going to some remote server, or to some server where the calculations are getting done, and then it's getting passed back to your screen, perhaps a plot or a table of numbers. So the only thing that's different about this architecture on the cloud, as opposed to any other place, is that the way you start this Dask cluster, you say you want maybe 30 workers or something, and you call something called kube cluster, which runs a cluster on Kubernetes, or maybe you call this gateway cluster, which is something cluster some administrator has set up for you. And if you run this thing on HPC, it's exactly the same, except that the way you start this cluster is different. So you might say Slurm cluster if you've got a Slurm job queuing system on your HPC, or PBS cluster or something like that. So the workflow, though, stays exactly the same. And if you actually just want to run this on your laptop, well, you can still take advantage of whatever CPUs you have on your laptop by saying just local cluster. So really the only thing that changes, like wherever you're using these tools, whether you're on your notebook or at your HPC center or on the cloud, is the way you start this cluster to give you a certain number of workers. So I'm just going to say a few words about netcdf. netcdf, if you just put netcdf files on the cloud, you often find that they don't have quite the performance that you expected, because on the cloud, you store data in object storage, which is the good part about object storage is there is a URL associated with every piece of data that you stick out there, so that you can just share data through a URL. The maybe not so good part is that there's a little more latency when you read data from those objects, and if you read lots of little data pieces from those objects, then it can take quite a while. And because netcdf was written for data on file systems, it can get kind of slow. So there's a nice blog post about this, about how we get around this. He talks, Matthew Rocklin, who's got a bunch of really nice blog posts about all sorts of things, talked about how, well, you can just put your netcdf files up there and you can make them look like files on a file system by using something called Fuse. That's kind of slow. Talks about some other things, and it suggests maybe it's time for some new formats for scientific data that do perform well on the cloud. So along came the ZAR format. It was developed by the genomics community, actually folks studying malaria and mosquitoes, believe it or not. And it was developed to address these problems with NetCDF on cloud storage. So it has a very simple format. It's developed in a community fashion. Each chunk is stored in a different object store on the cloud. So you read a whole chunk, you just read it in one grab. The metadata for all that data is stored in a simple JSON ASCII file, so you can grab all the metadata at once. It's got the same kind of filtering and compression, things like that NetCDF files have, and it works with Python using Xarray, just like a NetCDF file essentially would work. And so really it's kind of clever. It just, if you had a grid of information like temperature, it splits it into these different chunks, and the chunks are labeled things like 0.0, 0.1, 1.0, 1.1. If you want to read a specific chunk, some sub-region of this data, you can just go read, you want to read some specific indices, you can just go grab those chunks by their names. So you don't need some kind of fancy lookup to figure out where these chunks are located. It's just the names of the chunks themselves. And so if you look at one of these files on disk on one of these data sets, these are data sets, it's kind of nice also because all the metadata about the compression, what the compression types are, the fill values, the shapes, and all that stuff are in just a very simple file to read or edit. I guess you wouldn't edit that one actually. And then the attributes are in another simple file that contain things like long names and standard names and things like that. And this one you could just edit, like if you realized, oh, whoops, I got the wrong standard name here, you could just go and change it with your text editor instead of using NetCDF libraries to change some binary file. So, but the really powerful thing about this ZAR format is that it's driven by some of the folks in the community who are very well recognized and very smart. And so it's really nice to have a format that we're using to store, our ocean model data, our atmospheric, our climate data, hopefully in a format that is known by a community and not just known by one or two people, say at the HDF group, which is what is underneath NetCDF. So I really got started on this with the NOAA Big Data project because the NOAA Big Data project, I wanted to look at the National Water Model output, which is a model that that simulates flow on 2.7 million rivers. So obviously we don't have nearly that many stream gauges, but the water model is predicting stream flow on all the rest. And if you want to get this data, it was being pushed out. It is pushed out onto the cloud. So you can go to this bucket and look at it, but they're stored as hourly NetCDF files. And when I tried to access them, I found out it was pretty painful. And so when I tried to read these NetCDF files here, I'm just reading 23 gigs of data with a bunch of processors, and it took about 2 minutes to do this particular calculation. And when I used ZAR, I converted it to ZAR, it took 11 seconds. It took a little over 11 seconds. So you might say, uh-oh, do we need to abandon NetCDF and ZAR? Well, it's actually, we've learned a few things since then that makes it a little bit more fuzzy. One thing is that if you don't read NetCDF files with the NetCDF library, but you use the ZAR library and extract the metadata from these NetCDF files beforehand, you can actually get them to be cloud performant. And we wrote a little blog post on how to do that. So if you already have a bunch of NetCDF data and the chunking is reasonable, the chunk sizes need to be somewhere from 10 to 100 megabytes or so to be optimal. If you happen to have that, then you can actually have NetCDF files that perform on the cloud okay. The other thing is that Unidata is actually adding ZAR to be a new backend for NetCDF itself. So the next version of NetCDF that comes out will have support for ZAR under the hood. So you can just continue to use whatever NetCDF applications you have, but they'll be reading and able to be reading and writing ZAR in addition to the things that they can already read. So at this point, I'm going to, I'm going to go ahead and jump to a live demo that shows you how this stuff works. Hopefully you're still awake if you're like, what's all that NetCDF stuff? Hopefully this will wake you up. So actually I'm not, so this is a movie, but I'm not gonna show this movie. Hopefully I'm gonna do a live demo. So I'm jumping out to a, that's for if the demo doesn't work. So let's just go to, let's just do what you would do. Okay, and I'm actually gonna do something that you can in fact do yourself after this seminar. Please don't try to do it right now because when you do that, then you stop listening. But you could, it could handle it. And that's the other thing about the cloud is, you know, lots of people can do these things all at once, and it doesn't matter. There's lots of processors on the cloud, and you can hit these object stores with lots of people, and it doesn't slow things down lots of times. So I'm going to Google, I'm going to search for Pangeo Gallery. Make my font a little bigger. And so there's a lot of cool things here that you can look at that you can do with Pangeo. So these have been contributed by different folks. There's some cool climate demos. There's some really nice remote sensing demos. So if you are not into model output, but remote sensing data, there's a really nice Landsat tutorial. If you want to know more about all this stuff, there's a little tutorial gallery over here where you can learn, like take the DASK, sort of a quick DASK and X-ray tutorial and things like that, different components. But I'm going to jump down to this little one that I maintain here, this ESIP gallery. So these are all maintained by different folks. And I'm going to show you a calculation involving this Hurricane Ike simulation. So this gallery shows you the notebook. If I scroll down, you can see the notebook after it's executed, but I don't want to do that, so I'm not going to give it away. I'm going to click over here and launch the notebook live on Binder. So what's actually happening now is it's spinning up some cloud instances and downloading the software environment that is needed to run this this notebook. So it takes a little time because it's you know, if there's not any instances lying around on Binder, it's got to actually spin these things up and you know, creating new compute instances on the cloud. It's not instantaneous. And if somebody changed something in the code, then it has to actually rebuild the environment. Maybe that's what's happening here. Or actually, so I think maybe instead of waiting for that one to spin up, hopefully I could, I've got one maybe running over here. So this, normally it would come up like this. Let's see if this is actually still active though. Restart kernel, clear all outputs. Okay. So it looks like this one is running. So it should if we waited a little bit longer, this is like, you know, we put the cake in the oven and now we're taking it out. So we have this Binder environment that, again, you should be able to, when you run it, it should come up and look like this. You can click on, actually, if I close this, discard. Actually, let me just shut this down. I'm going to close and shut down the notebook. All right, and so you would come in at this level here after that Binder link finishes, and then you could click on this ESIP gallery, and then there's these two notebooks here. The Hurricane one is here. And again, I'm going to clear the output, restart and clear the output. So what's happening? Okay, so I should say something about this. This is the Jupyter Lab interface. This is the thing that you'll see if you run this on your laptop or on HPC or whatever. And you know, you have this little file browser over here. Over here, you have your notebook, and the notebook contains, you know, some text and stuff like that. But it also, these little gray areas contain code. And so when I execute this code cell, I'm going to hit Shift Enter. It actually executes this on the cloud, imports these packages. And you saw that change from blank to a 1. So we know that it executed that. Didn't, you know, we didn't really see much happening. But if we do this, we should see that we get a new cluster. Well, actually, if we execute this, we'll see that we have this cluster, and currently it has like no workers. Let's see here, let's go from like 4 to 30. So when we click adapt, we should see these workers come online. So now we asked for 4 workers, a maximum of 30. So it just gave us the minimum because it's not doing anything. And then as the computations, we get our more sort of serious computations going, this should kick up and give us more workers. So the other thing I'm going to do is I'm going to take this dashboard URL and put it over here, so we can see when our cluster gets going, we can see what's happening. So, okay, so here I'm going to read in, I'm going to say Xarray open this data set on the cloud. So I open it up and it's just reading some of the metadata, so it's pretty speedy. It's not reading all the data in this data set, it came back already. We can look at a particular variable like zeta, and we can see that it's 53 gigabytes. Okay, but it's packed into 11 megabyte chunks, as we were talking about before. We can see some of the attributes here. Sea surface height above geoid. So this is the sea surface during this Hurricane Ike simulation. And if we want to use the command line version, we can see that it's 53 gigabytes. Again, when I'm executing these cells, they're getting, when I type these cells, they're getting executed on the cloud, and the result is then coming back again to my browser. So here's the big calculation that's going to say, okay, take all the water level and the maximum, find the maximum over the time dimension. So for every grid cell in this model simulation, I want to find the maximum water level over time, right? I want to find the maximum water level during this hurricane. And this says just persisted onto these workers. And so I'm going to start this calculation. Actually, before I do that, I'm going to take this task stream, put it over. This is going to show us what the workers are doing. I'm going to put it over here. I'm going to take this progress one, and I'm going to put it down below so you can kind of move these windows around. And I'm going to close this down to give us some more real estate. So now I'm going to do this big calculation. Okay. So notice that I just take the max, and I don't have to do any kind of parallel coding here, right? But because I have all those workers and I have the data in chunks, and because Xarray is using Dask under the hood, it just starts crunching all that data. And so each one of these little tasks here, each row is another processor, and you just saw we got the other ones kicking in because it said, whoa, this is a big computation. And so here's all these different workers crunching the data. They're reading little chunks of data from ZAR. They're computing the maximum of each chunk, and they're putting them together. And you can see from this dashboard too that there's hardly any white space in this whole blue stuff, right? So like the workers are busy all the time, and they're not just sitting around waiting for something to do. They're all, busy crunching. And so, not only do I not have to have enough memory, like I don't have to have this much memory on this machine because they're being computed in chunks, but because we have lots of workers, the computation could get done a lot faster. So now it's done. And so we just computed the mean, in about less than a minute. So the maximum water level in less than a minute. And now we're going to visualize that data that we got back using these holoviz tools. So the key thing here is we get this mesh, data, and we say, just rasterize that data onto this plot that's, I'm going to close these down so we can see a little better. Give me back the data on a 600 by 400 pixel screen. So that's what it's done here. So it's rendered all those 9 million nodes of data onto the 600 by 400 pixel screen, right? It's just giving us back those pixels. So you're like, well, that kind of stinks because we can't really even see what's going on down here in the Gulf of Mexico where the hurricane hit. But we have these little tools over here, and we can zoom in. And when we zoom into this region, it'll re-render the graphics to that 600 by 400 on the back end. So those processors are kicking in, re-rendering the data. We can go as far as we want, right down to the original resolution of this grid interactively without moving a lot of data. And this is kind of like, to me, this was like the killer app, because not only can we crunch this data really quickly, we can actually visualize it in the browser in a really efficient way, right down to the highest resolution of the data. And this is just showing that not only can holoviz do things like do that mapping nicely, but it's very simple to, all you have to do if you want to get some data and plot it up, here we're actually picking a particular index, giving me all the times at this particular index. And then I just say HV plot, and I want the x-axis to be time and put a grid on it. And I get this nice little plot here. And I can hover over this and find exactly when the peak of the hurricane the peak water level for this particular location. And you can see again that it was pretty speedy because the data is chunked. So that concludes our demo for today. I am going to now be a nice guy and close my notebook so that I release those workers so somebody else can have them. And I'm going to go back to my PowerPoint and just finish up here. So you might, okay. Well, I'll just go, I'll just blast through these. All right, so it's not just for model output, as I mentioned before, that you can use this really effectively for large collections of satellite data, and there's lots of satellite data and other imagery that's being put onto the cloud. So if you want to access efficiently, if you've got there's a ton of satellite data sitting out on Amazon on the cloud, the best way to access it is to get on to Amazon and compute to that data, right, with a bunch of processors. There's a great blog post here by Scott Henderson. One of those, and if you go back to that gallery, as I mentioned, his notebook here that he describes in this blog post is one of those gallery demos, and you can run it yourself. This is just a scene from that blog post. And other folks are picking it up. It doesn't really have to even be geospatial, right? These same techniques using data, chunked data with lots of processors on the cloud is a powerful approach. And even if you don't care about chunked data, you just want to run like a bunch of simulations that some parameter set or something like that, DAS can also do that kind of parallelization. So it can do sort of embarrassingly parallel stuff as well. So you can really use DAS for just about anything. And it's not even just, it's not just for big data. This is actually from a machine learning class that we taught where everybody was logged into Pangeo using Pangeo for the interface, and that meant that nobody had to install anything. They just came with a browser and everyone could do the course. In fact, we have a machine learning class going on right now, Machine Learning Mondays, that's using this as well. I love this slide. I thought I removed this slide, but it's kind of funny. It's this is the British Met Office receiving an award for their work on Pangeo. And I just like seeing members of our community looking like that because the USGS got I think was voted the worst dressed agency. Okay, so I think I'm going to skip over the details of Pangeo and AWS. I don't think you guys care about that. I think this is important though, overcoming barriers to adoption. So you might be thinking, how do I do this? And what's it going to cost? And wait a minute, my HPC is free and I have to pay for the cloud. How does all that work? And those concerns are real. Computing costs at institutions are usually buried in overhead. The institution buys a new computing center. And then all you have to do as a researcher is, maybe pay for a little bit or buy a rack or something like that. You're not paying for the real cost. So I don't know how institutions are going to deal with that, but I think they're going to have to because there's a lot of scientific work that's going to be only effective on the cloud. And then how do you learn how to do this stuff? Well, we have workshops and we have those tutorials, and there's things like the Ocean Hack Week and things like that. But I think we really need actually something like Pangeo Academy or something like that, like patterned after the Khan Academy. And then learning how to deal with these new data formats. So if you are interested though, if any of this stuff looked interesting to you, you can go to pangeo.io and try out some of those demos. Like I said, just click the binder links. You can look at the notebooks that you think are interesting, and then click the binder links, run the demos. There's a bunch of really neat articles at Medium on Pangeo from different members of the team. You know, there's a Gitter channel here where if you get into it, you know, you can just chat sort of in real time with folks. It's a very active and responsive community. And if you want to try this out, there's some instructions, there's some links here, then I'll share this slide deck. But you could also just Google like Pangeo HPC if you're interested in installing this yourself at your HPC center. It actually, you can install it yourself in like 20 minutes. You don't even need the admin to help you. So you can do it all just locally in your own environment. I was kind of blown away when I realized that I had that capability, and I was able to start actually working remotely at the compute center without pulling anything back to my local computer. So even if you just do that, it can be a game changer. And of course, running on AWS, as we showed here, there's actually a really nice package that helps you, for this, yes, you would need some computer admin to probably help, but there's a nice package that makes it pretty painless for that admin to get things set up. So you could set up like a departmental Jupyter hub, or, for some collection of projects, you could set up a Jupyter hub for your everyone associated with a particular project. And then I just threw this in here because rechunking your data can be tough, or it was tough actually, before this package called Rechunker. So with that, I'll close out and answer any questions. Thank you very much.
Thank you. So we'll open it up to questions. So feel free to raise your hand, or you can enter in the chat box as well. So we have one from Val. He asks, does ZAR work across cloud providers? Can ZAR data exist as a file system type format?
Yeah, that's a great question. So actually ZAR works great on disk as well. And it's kind of like I've been writing stuff in ZAR since I first realized it. It works great because it's completely parallel, writing. You don't have to worry about some fancy library that, parallel version of the NetCDF library or something like that. But it works on any cloud. Right now, it's you can read it. You can only read it using Python and Java. But when Unidata finishes their NetCDF-C library implementation, you'll be able to read it with R or anything that can wrap C. So pretty much anything. So that's the kind of downside of ZAR right now, is that unless you're a Python person, you might not be so happy. But again, that'll change probably in the time scale of maybe 6 months or so. Unidata will be finished. They're pretty far along. Oh, and I should say, so you might, yeah, so I don't know if this was part of the question, but you might be thinking, okay, wait, so what if my data's not on Amazon cloud, but it's on like Google Cloud, or it's in the Western region of, Amazon, and my compute is in the Eastern part or something like that. So, which are also concerns, right? Like nothing is ever going to be all in the same place on the cloud. And so there's this project called DAS Gateway. Actually, it lets you set up a cluster on these different regions and different computes. So there's actually a demo that you can find, multi-cloud demo of Pangeo, where you're just using a local notebook on your local laptop, but you're connecting to a DAS gateway on Google and another one on Amazon. And on each one of them, you're crunching tons of climate data and then comparing the two. And all you've done is, used your local notebook and a URL that connects you to one of these DAS clusters with an environment that's capable of doing the analysis that you want to do. It's pretty amazing.
Great. So do we have any other questions?
Okay.
So Val has a follow-up question. He says, do you have the sense that ZAR will be here to stay? Is object-based storage something that will always be preferable in a cloud setting, or just what AWS, MSFT, and Google have done?
Yeah, so I mean, I think because it works so well on disk also, I think it's going to be here to stay, and especially with Unidata adopting it as a backend. And I really, as I sort of mentioned, I really think it's great that we are storing data that we want to archive in a format that can be like understood, you know, and by more than a few people.
Alyssa, you're muted.
I saw somebody else had a question.
Yeah, just a quick question. So for those of us that are a bit more comfortable just coding on local machines, based on just we're not dealing with larger data sets.
Right.
I've found that I'm having a hard transition going to notebooks, but should I just get over it? Like, are we just moving towards the fact that large data is going to necessitate working on online notebooks rather than, because so I spent a life at sea for about 5 or 7 years where the connectivity is just not there.
Right. Yeah, no, I mean, and you don't, yeah, you don't have to use notebooks. I mean, you can use just regular Python code too. Like, you know, you could, but yeah, if you're in a situation where you don't have the internet, yeah, you know, yeah, it's not gonna, you know, you're gonna be running locally. But you can use the same approach, like right, I mean, I think using the notebook, you can use the notebook, you can use Jupyter, but still run like Python code, you know, so.
Yeah, I just find a lot of the time with Jupyter, the issues that I run into is different package releases that are integrated into Jupyter that aren't necessarily, so you're actively working on your machine with a newer release, and then you try a code on Jupyter and it just doesn't work, and it's a frustration for not being a
Yeah, I mean, I think what you're expressing is like a frustration with like Python packaging in general,
Yeah.
maybe, and that's definitely a thing for sure, at especially when you're using kind of cutting edge stuff. I'm sure you're aware that, like, you know, Conda and Conda Forge have made things a lot better, and you know, so if you look at if on that last link when you get the slides, or if you Google Pangeo setup on HPC, which is actually really the same thing. It says Pangeo setup on HPC, but it's really basically the same thing that you'd want to do to set up a sort of stable environment on your local computer. It uses you know, custom environment that's all using packages from Conda Forge, so they're kind of guaranteed to play nice together. And there's, you know, but there's some things that you can easily get yourself screwed up with packages from different channels and things not working, and extensions that didn't get installed, and, you know, things like that. So yeah, it is really best to follow like a best practice. You really need to follow like a best practices guide, and you know, Pangeo I think is a good place to get one. And if you do that, I don't think you shouldn't have those problems that you're talking about.
Yeah, perfect. Thank you.
Just make sure we don't have any final questions here.
I will say one thing that I mean, okay, yeah, if there are more questions, I'll take the questions.
Nope, I think that's it.
So you know, just because, yeah, there's a lot of people who are not using, you know, like big data. I don't care. I'm not working on terabytes of data. I've just got some, you know, some observational data or whatever. But we did, you know, one other advantage of the cloud is, so we had 3 different centers, and we are all collecting oceanographic data, you know, time series, trajectories, you know, glider data and stuff. And we were processing our data, you know, in sort of different ways, and we were trying to be kind of the same, but you know, sometimes we didn't pass the algorithms around as, you know, as well as we should have, and things like that. And so we thought, we did a little experiment, like, hey, what if we just moved our observational data to the cloud and tried, you know, using Pangeo to do our processing of our, you know, raw data into scientific data, and then, you know, the standard QC and all that stuff. And, you know, and the one advantage of that is that we're all using the same environment, and we can all see that, like, we all know where the data is, you know. And it's actually, so it has benefits sort of beyond just the big, you know, data piece, because you can really start to share everything. Like if you're using the same environment, I'm running on the cloud, if I'm running on Amazon and Pangeo, anybody can reproduce that environment pretty quickly.
Perfect. Well, yeah, I think that's all the questions we have. So
I see something from Guy Knoll. There must be.
Yeah.
I should look at the chat myself here. Hold on. Yeah. Okay. Massimo. So Massimo says, with Dask, he said this to me privately. With Dask, we already get to use all the CPUs. You may mention it is possible to do most of the stuff on the GPU. That's true too. If you have a GPU, either locally, or you've asked, or you are running on Amazon and you've asked for a GPU instance, you can do a lot of this stuff. It's super, you don't need to have a Kubernetes cluster. You can do stuff super fast by using the GPU. And you can even combine like the GPU, like multiple GPUs to do stuff even faster if you need to. Yeah, thanks, Massimo.
So sorry, why I didn't see that one.
Yeah. Oh, Val has another question.
Yep, Val has another.
I might just unmute myself because I have so many. I think this is a great talk. And I thought I would just tell everyone that this summer we installed actually a Pangeo instance on a local cluster here at CCOM. But honestly, I don't think any of us have had time to actually tinker with it very much. But if you're interested in it, get in touch with me or Mike. Mike Sleep. But the question I had was about HoloViz. I'm not familiar with HoloViz.
Oh, yeah.
And maybe you could talk more a little bit about what's good about it and how it compares to like traditional Matplotlib and
yeah, it's fantastic, and so few people know about it. I don't know. It's I know partly about it because my daughter used to work on that group. She's since moved on to another tech company, but they it's amazing because basically instead of .plot, like on X-ray, you have an X-ray object. I don't know if I guess I should have mentioned that a little bit more clearly, but you can just do a .hv plot, and instead of just getting a static plot, you get these live plots that are, that you can zoom in on, that you can hover over, that automatically, do projections and bring in tile services, to give you a base map and, not a dynamic base map that changes when you zoom in, so you can, see what's going on in your estuary. It's to me, it's like it's another game changer because, we didn't even have a way to explore like this data and even if you have a time series, like you have a complicated time series, you want to be able to zoom in and hover and see what's going on, and the HoloViz gives you that capability. It also gives you capability to create these sort of dashboards. So like that last plot that I showed, with the zoom on the Hurricane Ike maximum water levels, you can just turn that into a web app, actually, that's running the Python code on the back end, and all the user sees, are those controls and maybe some widgets. And it's a way for like a scientist to actually create a web application super simply just using Python. And then, and I think that could be a game changer going forward, because if we as scientists can kind of make these like kind of, simple applications, then, if they get popular or people really like them, then we turn it over to the web developer to get some, fancy finishing. But it's a fantastic way to, share something with people who maybe don't know Python interactively, and they can still explore, big data or do some kind of analytics or whatever you want through this through a web app.
Yeah, that's great.
And that's
Thank
called
you.
Panel. Yeah.
Cool. Thanks.
Yeah, check out the HoloViz. HoloViz has got some amazing demos if you go check out their gallery.
Okay, so unless you have any other private questions, I think that's all we have. So thank you, and let's thank our Dr. Signell once again. And I hope everyone has a great weekend. We'll see you next week.
Thanks, Alyssa.